Now another method of preparation of benzaldehydes is the reaction between carbon monoxide and HCl gas in presence of a catalyst mixture consisting of aluminum chloride and a small amount of cuprous chloride. Now, to a solution of benzene in ether, carbon monoxide gas and hydrogen chloride gas are bubbled through, and the reaction takes place. HCl donates H positive to carbon monoxide. Carbon monoxide is having this structure C double bond O, 2 lone pairs over oxygen and 1 lone pair over carbon. Now this lone pair is donated to H positive supplied by HCl. Now Cl negative from HCl is taken up by aluminum chloride, which is a Lewis acid and can provide a vacant orbital over aluminum, so that into this vacant orbital Cl minus forms a bond and AlCl4 negative is formed, H positive combining with the lone pair of carbon, and that species, it is called the formyl cation. So formyl cation is a resonance hybrid. The lone pair over oxygen atom is given for bonding, so that positive charge of carbon is neutralized and positive charge now comes over oxygen atom. Now, so it is stable, it can undergo electrophilic attack over the benzene ring, this pi bond shifting in between this carbon and this carbon, so that the positive charge is neutralized, and we get an intermediate, a carbocation. This can be stabilized by resonance, and again it reconverts back to the benzenoid structure by removal of an H as H positive from the CH bond, shifting in this direction. So minus H positive and benzaldehyde is formed. This is Gattermann-Koch reaction. So carbon monoxide and HCl gas are the reagents. Formyl cation is formed. It is an electrophile, attacks the benzene ring, and then benzaldehyde is formed. Now preparation of aromatic ketones. One method is the reaction between a phenyl magnesium bromide and a methyl cyanide. Now addition takes place, phenyl part becomes the negative part, and CN bond polarizes, so that N negative is formed, and MgBr connects to N negative, and the phenyl negative part connects to the carbon. We get double bond N MgBr, which undergoes hydrolysis. This part is broken. N becoming negative connects to H positive, and Mg positive connects to OH negative, HOH. Then this bond is broken. All the bonds are broken. The sigma and pi bonds are broken. One molecule of H2O acts like this. Oxygen is divalent. C double bond O is formed, plus NH3 from this compartment and MgOHBr from the last compartment. Now acetophenone, this compound is called acetophenone. Acetophenone can also be prepared by the reaction between benzene and acetyl chloride. HCl is removed and the COCH is getting connected. The reaction takes place in presence of anhydrous aluminum chloride. Now benzaldehyde gives the usual reactions of aldehydes and ketones. It forms hydrazone with hydrazine, oxime with hydroxylamine, and semicarbazone with semicarbazides. But it does not have an alpha hydrogen because the alpha carbon here is the carbon of the benzene ring. All the valencies are filled. There is no H here, so there is no alpha hydrogen. So it will not give aldol condensation reaction, but it can give a Kainisarose reaction. Now, if a ketone containing alpha hydrogen atom is there, then the reaction can occur between benzaldehyde and acetophenone. A molecule of water is removed, and then we get an aldol type product, condensation product with sodium hydroxide and a temperature of 293 Kelvin. Since there is no alpha hydrogen, it gives Kainisarose reaction. 2 molecules of benzaldehyde plus a molecule of water. The reaction occurs in presence of concentrated NaOH first, and then acidification, because the sodium salt of the acid is formed, which is on acidification gives the free acids. The CHO group is reduced to CH2OH, and again it is oxidized to COOH. So self-oxidation reduction in presence of concentrated sodium hydroxide, that is Kainisarose reaction. Now, if two different aldehydes without alpha hydrogen atom are used, the nature of the product depends on the electronic effects in the reactants. Now, the mechanism is initial attack of OH negative on the carbonyl carbon, that is a nucleophilic attack. Now, this nucleophilic attack depends on the extent of positive charge carried by this carbonyl carbon. If we use benzaldehyde and formaldehyde, both containing no alpha H atom, in the case of benzaldehyde, there is flow of electron density towards the carbonyl carbon from the benzene ring. So this carbonyl carbon is less positive, so nucleophilic attack is not so easy at this carbonyl carbon. It is easy at the carbonyl carbon of formaldehyde, so OH negative attacks that species. And then CO bond polarizes to give O negative. Then the benzaldehyde molecule comes in the scene. The CO bond polarizes the positive charge of carbon. Here H has H negative, that is important. A hydride ion is being shifted towards the carbon, neutralizing its positive charge, and we get CH bond, O negative. And here we get this bond, negative charge shifts in this direction, means the lone pair here becomes a bond pair here, so that the valency of carbon is now maintained for here. And since this anion is obtained from an alcohol, this OH bond ionizes and H positive comes here, and this becomes CH2OH. So when formaldehyde and benzaldehyde are mixed together and subjected to Kainisarose reaction in presence of concentrated sodium hydroxide, we get formic acid and benzyl alcohol, not benzoic acid and methanol, because the initial attack of OH negative is easy, and again it is electronically made easy because there are no groups which will diminish the positive charge of carbonyl carbon of formaldehyde, but in the case of benzaldehyde there is minus some effect of the aldehyde group which withdraws electron density from the ring, and the carbonyl carbon is less positive. Now coming to the resonance structures of aromatic ketones. The structures are similar to those of benzaldehydes. CO bond polarizes, this bond comes here, positive charge here, and then this pi bond shifts in this direction, positive charge becomes here, you get positive charge here, then this bond becomes migrated in this direction, positive charge comes here, and this bond migrates in this direction, positive charge coming here, then this lone pair comes as a bond pair here, so we get the canonical structure, final canonical structure, which is same as the starting, but only difference is the positions of the pi bonds are changed. So 1, 2, 3, 4, 5 canonical structures may be drawn. The ortho and two ortho and para positions are carrying positive charge. So like benzaldehyde, acetophenone also undergoes electrophilic substitution, preferentially at the meta position. The ring is deactivated by withdrawing electron density by the COCS3 group. It is minus M effect of COCS3. So nitration of benzaldehyde, we get metanitrobenzaldehyde with concentrated nitric acid and concentrated sulfuric acid, and acetophenone on nitration with concentrated nitric acid and concentrated sulfuric acid, we get metanitroacetophenone. Now some in-text question: arrange the following in the increasing order of their reactivity in nucleophilic addition: ethanol, propanol, propanone, butanone. Now there are two important effects. One is steric effect and the other is inductive effect. Now ethanol is acetaldehyde. It is CH3CHO. And propanol is CH3, CH2, CHO, C double bond OH. Then propanone is acetone, CH3, CO, CH3, and butanone is CH3, CO, CH2, CH2, CH2. Now in acetaldehyde there is only one methyl group, the other group is hydrogen. It is exerting no other steric effects. So hydrogen is a small group, so there is no steric effect from the part of hydrogen, but methyl can exert steric effects, and again methyl can exert 1 plus I effects. Now when we come to propanol, the ethyl group is bigger than methyl group, so a little more steric effects. When we come to propanone, there are two ethyl groups and also the combined steric effect of two methyl groups and the combined plus I effect of two methyl groups diminish the positive charge, partial positive charge over carbon greatly. And here we have one bulky group, that is ethyl, and then a small bulky group So the two groups exert greater steric effects in combination, and again there are plus effects of these groups. So largest steric effect and plus effects are observed in the case of butanol. Then less steric effect is observed in the case of propanol, and then lesser steric effect is obtained in the case of propanol and ethanol, the least steric effect, and plus effect is also maximum in the case of butanol, and the plus effect decreases when we come to propanol, because ethyl group can exert a greater plus effect than methyl group, and here ethyl group, even though it exerts a larger plus effect, it is not so much greater than that exerted by two methyl groups. So, and again here steric effect is comparatively less, and the least steric effect and index effect are observed in ethanol. So the reactivity order will be ethanol greater than propanol, greater than propanol, greater than butanol. So ethanol, propanol and butanol, these ketones contain two alkyl groups connected to carbonyl-carbon. So the partial positive charge over carbonyl-carbon is more diminished than aldehydes, in which only one alkyl group is connected to the carbonyl-carbon. Alkyl groups diminish the charge by plus effect, again due to the bulky nature of alkyl groups in ketones. The incoming nucleophile is sterically repelled more than in aldehydes, which contain only one alkyl group. So generally we can say aldehydes are less sterically hindered, and plus effect is less compared to ketones. So aldehydes are more prone to, more easily subjected to nucleophilic attack than ketones. Now coming to the case of benzaldehyde, para-tolualdehyde, para-nitrobenzaldehyde and acetophenone. Now this is acetophenone, this is para-tolualdehyde, this is benzaldehyde, and this is para-nitrobenzaldehyde. When we come to para-nitrobenzaldehyde, in all these compounds the CHO group is common, so its minus M effect is common in all these groups. Then nitro group can exert a minus M effect, so that the pi electron pair here shifts in this direction, this pi bond shifts in this direction, this pi bond shifts in this direction. We get O negative and positive, and the positive charge at the alpha carbon, which exerts a minus I effect, so that this carbonyl carbon is made more positive than these cases. So para-nitrobenzaldehyde is the compound which gives a higher extent of nucleophilic attack. Then comes benzaldehyde. In the case of para-tolualdehyde, this methyl group can exert hyperconjugation, increasing the electron density in the ring as well as in the CHO group, so that the carbonyl carbon gets electron density via hyperconjugation. In the case of acetophenone, the bulky phenyl and methyl groups, and also the plus effect of methyl group, diminishes the positive charge to a greatest extent, so that the nucleophilic reactivity will be least for acetophenone due to steric effect of two alkyl groups, and also due to the plus effect of methyl group. And so the order will be para-nitrobenzaldehyde, which is having the highest reactivity towards nucleophile, and then benzaldehyde number 2, and then para-tolualdehyde, which donates electron density by the hyperconjugation, and the least for acetophenone, since it is a ketone, bulky groups. Methyl group is comparatively bulky, phenyl group is also a bulky group, so nucleophile cannot easily enter towards the carbonyl carbon, and again methyl group shows a plus effect that will neutralize the partial positive charge or carbon, and again methyl group there can exert what is called hyperconjugation. This CH bond shifting this direction and this shift. So this hyperconjugation also can decrease the extent of positive charge carried by this carbonyl carbon. So that is enough. We shall see the next question parts in the next video. Thank you.